Hi guys, welcome back to Data Every Day. Today we're looking at a data set of houses in Perth, and we're going to try to predict the price of the house based on a series of 18 features. So let's hop into the notebook. We're going to use NumPy and pandas for working with the data. Then for pre-processing, we'll use the train test split function and standard scalar from sklearn. And our models, we'll use 3 linear regression models today. One with no regularization, one with L2 regularization, and one with L1 regularization. So let's go ahead and import everything and load in the data using pandas.read.csv. We can grab the file path up here. I'm going to paste it in. Let's also zoom up a little. And we can take a look at the data. So we have 19 columns and 33,000 rows. So a good amount of data to train on. And I can see we have at least one missing value in here. So let's get a little more information with data.info. And yeah, it looks like there's a few missing value columns in here. We also have 5 object columns. So let's start pre-processing. I'm going to create a function called preprocess inputs. It's going to take in a data frame. And for now, all it will do is copy the data frame over. So we'll return the same one down here. And I'm going to call the preprocessed version of data x. So I'll pass data into our function, get back the result as x, and now this is the copy we'll perform the preprocessing on. So the first thing to worry about, I think, is feature selection, dropping any columns that we might not need, or that we know we won't need. Certain candidates for column dropping would be either columns with too high a number of values, high cardinality columns. If there's a column, the categorical column with a really high number of unique values, like in the tens of thousands, even in the thousands, if we were to encode it with one-hot encoding, it would add so many columns to our data set that it would just slow the model down way too much. And additionally, the more unique values you have in a column, you can consider maybe the less useful it is for making predictions, because as the number of unique values approaches the number of rows you have, there becomes less and less of a way for the model to draw similarities between training examples using that column. So let's check this out. We can make a dictionary that's going to map a column name to the number of unique values in the column. So I'm going to take the length of x subcolumn dot unique, and I'm going to do this for every column, not just in x.columns, but just the object columns. So x.select dtypes object dot columns, and we can see the number of values in each of these object columns. Now the address column is the only real issue here. 33,000 unique examples. That actually seems like it's about 99 duplicate values. So it's almost exactly the number of rows. Let's just go ahead and drop it. It's too high cardinality. So drop high cardinality address column. So df equals df.drop address from axis 1. It's gone. I won't have to worry about that anymore. The remaining value, remaining number of unique values is quite manageable. If these are nominal features, we can just add a few hundred columns onto our dataset. Not the same as adding a few thousand. Okay, so then we should look for missing values. We know we have some in here, so we can get a sense of this with x.isNA. This will give us a true-false matrix of missing values, so a true means a missing value in a given location. We can then sum over the rows to get the total number of trues in each column, so the total number of missing values in each column. So this is good for seeing what's remaining, but if we want to actually understand which of these might be like too many missing values, it'd be better to take the mean instead, which will sum up all the truths and then divide by the length of the column. So we'll get the percentage of missing values in each column. And it looks like this column is the only one with a dangerous amount. Generally, you can drop columns with more than 25% missing values. This one has 32%. So let's go ahead and drop this one. The reason we want to drop it is because if you have too much fabricated data in your dataset, it can actually inhibit the model's performance. So drop high missing value column. I'll say over 25%. And then df equals df.drop nearest school rank axis 1. Okay, so the remaining missing value columns are 9% and 7%. That's very manageable. We can just fill those. So let's use sum again to see which those are. So garage and build year. So when filling missing values, you have to consider what type of column it is. Garage here, it looks like a count column, or an integer column. So it is a continuous column. This is the number of garages, I believe. I wish there was a little more information. Maybe there is. Let's see. We can take a look. Oh, what is this? Let's see. Can I just search house or any house? I just want to see what kind of information they offer. Garage. Okay, I'm not sure exactly. There's not too much information. But okay. Well, I'm just going to assume it's a count column. But let's maybe get a little more information by looking at which types of values we have in the column. So I'll look at the unique values. And yeah, okay, so this is really difficult. It's hard to say if this is a count column. It's definitely not the number of garages someone has, because there's no way someone has 50 garages, 99 garages. So I wonder if it's a type of garage, because if it's a type of garage, then this is a categorical column. So this is problematic. When it comes down to something like this, the best thing to do is probably try both approaches and see which one works better. So we could encode this as, you know what I'll do? I'll make a separate flag in here called garage. And if it's continuous, excuse me. If it's continuous, then we'll fill the missing values with the mean of the column, and we'll leave it as that, like that. If it's categorical, then we will fill the missing values with the mode. Or actually, we don't have to fill the missing values at all. We'll just one-hot encode it right away. So let's say this. Okay, so if garage equals continuous, then we'll fill the missing values with the mean. We take the garage column, type .fillNA to fill the missing values, and we'll fill it with df sub garage dot mean, and we'll set that equal to the original column, like so. Okay. The other one we always want to fill, that's the build year. Build year we know is continuous. I don't know if we should do mean. Because they're integers, we might just want to do mode. The most frequently occurring integer. Let's do mode. You have to subscript with 0 for doing mode because this returns a pandas series instead of an integer. Okay, so I guess let's take the build year column, which is the other one with missing values, and fill this with the mean. Because a year column is continuous, you can think of it as a measure of recency. So there is meaning based on like how far into the past you're going. And it's okay that we'll get a decimal value. If you really want, you can do median or mode. Yeah, why don't we do median for fun? Alright, we'll take the, let me just say this, fill missing values. and then we'll take the build year column and call .fill in A with df sub build year dot median. Okay, let me just double check that this returns. Okay, it returns an integer, so we're good. Alright, and we'll set that equal to the original column. So we're only going to fill this in the case that it's continuous. And I'm doing mode, I guess I'll do median actually. Alright, so by default garage is continuous. Alright, next let's extract the date features. So we have a date column here. That's date sold. And it has month and year. And so those are two continuous features hiding in a string. So let's take them out. Let's take date sold. We'll say extract date features. So we're going to take the column and we're going to turn it into a datetime column with pandas.toDateTime. What's nice about datetime columns is you can datetime objects have attributes month, day, and year. You can just type dot year on each element and take out the element as an integer already. So let's take the column and set it equal to a datetime version of itself. Then we'll create a new column called date year. That will be the original column with a lambda function applied to it. For every x, we get x.year. We'll do the same thing for month. We're going to change this to month, and for every x, we get x.month. Then, when we're done, we can drop the original date sold column, since we took all the information we need out of it. We may run into an issue here. So let's see. No, we didn't. Yeah, it doesn't look like we did. Looks like it took out the integers properly. The issue I was afraid of is the format of the columns a little weird, but toDateTime is a smart function that can figure out the format most of the time. Alright, so last thing to do is look at this. We have some categoricals, and these happen to all be nominal, meaning there's no ordering between the values in them. So we'll one-hot encode the remaining categorical columns. So let's take one of them, called pandas.getDummies, and then take that column, and you'll see that each unique value in the original column gets its own column, and there's a 1 corresponding to the original value of that example, and all the rest are going to be zeros. So this takes care of missing values on its own, because if there's missing value, you'll just have all zeros straight across, no 1. So we don't even have to fill missing values for categoricals. Not that we have any more, but if we are going to have garage as a categorical variable, then we won't need to fill it like this. Alright, so now let's one-hot encode the nominal features. And so there's 3 of them, right? These 3. I also want to point out we can include a prefix here. So this is nearest station, I think. So if we include station as the prefix, you'll see that station just appears at the beginning of each column name so that we know where these columns are originally coming from. So let's up here. For every column in, and we're going to use these as the list. So we'll just clean this up a little. For each of these columns, we're going to create some dummies with pandas.getDummies for the column, and we'll give it a prefix of the column name. We'll keep it the same as the column name. Then we will take the dummy columns and put them onto the original data frame with pandas.concat for concatenate, concatenating df and dummies side by side, so axis 1. And then we can drop the original column from which we created the dummies, since we no longer need it. Alright, now we should have a whole bunch of one-hot columns at the end. So we have 500 columns now. And I did realize something. There actually is another hiding categorical in here. That is the postcode column. Postcode is numeric. I mean, it's encoded as a numeric value, but these are independent values. They're codes. So it's not meant to be interpreted as one is greater than the other. They're supposed to be independent. So let's also encode postcode in this list here. Okay, so we have 677 columns now. And what is next? Okay, so I guess we'll just split the data frames, scale, and then train. So split df into x and y. Because the data is fully numeric, no more missing values, we can now split the target off from the data frame. The target here is price. That's what we're trying to predict. And we're going to drop price to get the feature data. So the rest of the data is getting stored in x. Then we'll do our train test split. That will return 4 new sets of the data: x train, x test, y train, and y test. For this, we'll use the train test split function from sklearn. We pass in x and y, specify a train size. Let's send 70% of the data to the train set. Shuffle equals true. That's on by default. But since we're shuffling, we're going to shuffle before the split. That's what this function does. We're going to include a random state to ensure the shuffle, and therefore the split is always done in the same way. And then let's return these 4 sets of the data from the function. And take a look at x train. So this is 70% of the original data, and it no longer has the price column on it. The price column will be stored in y train. Alright. So last thing to do is scale the data. What is this? I don't know what these mean. I'm not sure if these are supposed to be categorical or numeric. I'm going to assume it's numeric. Distance. Okay, it's distance. All right. Yeah, so numeric. Okay, so we're treating garage as continuous, as numeric. So everything is in numeric form. Let's scale x with a standard scaler. So we're importing this from sklearn. Scaling is just giving each column the same range of values, which really improves the performance of many models. And the standard scaler is going to shift and scale each column so that they have a mean of 0 and a variance of 1. We'll call scaler.fit on xtrain, only fitting to the train set because we want to pretend we don't have access to the test set when we're doing the pre-processing. And then we're going to transform xtrain using scaler.transform. Now this returns a numpy array, so I want to keep it in a data frame format. So I'm going to turn it back into a data frame afterwards and keep the indices and column names the same. So index equals xtrain.index and columns equals xtrain.columns. And I'll do the same thing for xtest. So let's go in and change these to xtest. Alright, so the data is now scaled. Each column has a mean of 0 and a variance of 1. So let's start training. So what we're going to do is create a dictionary of models. The first one, what I'm going to do is map the name of the model to the actual instance of the model. First one we have is just linear regression. And that's going to be a linear regression object from sklearn. Then we have ridge regression, or L2 regression. Well, L2 regularized regression, we should say. And that's going to be the ridge regressor from sklearn. Then we have lasso regression, or L1 regularized regression. And that's going to be the lasso regressor from sklearn. Alright, so I'll just indent this one to match up with the others. And then what we'll do is just iterate through this dictionary for every name and model in models.items. .items returns the key value pairs as tuples, so we can iterate through two at a time. And we're going to fit each model to the train set, xtrain, ytrain, and then print out a confirmation message that says the model trained. There we go. When this is done, we'll get the results down here. We can just iterate through again for name and model in models.items. And we can print out the score of the model, the r² score in this case. r² score. Let's put the name of the model, followed by the r² score for that model. We'll display it to 5 decimal places and format this with model.score xtest ytest. Alright, so at the looks of it, ridge regression is doing the best. Regular linear regression is doing terribly. The best r² score you can get is 1.0. It's basically a measure of how dispersed the data is around your fit. And it can be really bad. There's no lower bound on it. It can go really deep into the negatives. You can see linear regression without any regularization not doing well. Just a little bit of regularization though, and you can see it's doing quite well. So my guess is it's overfitting here because of the high number of columns that we have. Regularization can really work to address overfitting. So I noticed that the L2 regularization is doing a little better. And the real main difference between these two, L2 regularization tries to minimize the squares of the weight coefficients. So it has the effect of really trying to bring down huge weights. It cares a lot about big weights and trying to bring them down. And it cares about big weights much more than it cares about little weights. The lasso regression, L1 regression, tries to minimize the absolute values of the weights. So it cares about all weights equally, big and small. And so L1 regression has the effect of being able to do automatic feature selection by bringing some of the weights down to 0. Some of them can come right down to 0 and eliminate the feature completely by multiplying the input by 0. Whereas r², it's harder to do that because the model doesn't really care about these tiny weights. It really wants to bring down the big ones. So let's take this one, which is our best performing model. We'll make it a new one. We'll call it ridge model. And we'll specify the alpha value. This is the regularization strength. So how much regularization are we applying? How much do we care about minimizing the squares of the weights? And we'll take the model and fit it. And we'll print out the r² score. Ridge model.score. Alright, so interesting. Alright, oh yeah, so okay, we gave it 10 strength. By default it's 1. If we bring this down, it looks like our value is going down. As we make this smaller and smaller, we should be getting smaller and worse results. Wow. Alright, it's really getting bad. However, we make it stronger. If we make it so 1.0 is just this. If we make it 10.0, we do get a little better. How about 100? No, it went down again. So 10 is the best. Maybe 15. Not much difference. 16, 17, 18. Oh, why am I going so slow? Let's try 50. No, it doesn't seem to be working, so let's just keep it around 10. And the last thing I want to do is try to change this. Try to use garage equals categorical. So if garage equals categorical, then we'll do the same thing our garage. Okay. So over here, we'll try it with garage equals categorical. So now garage will not have its missing values filled, and instead it will be encoded as a nominal feature. So let's see how that improves, how that changes the performance. So before we had this, and we now have better performance. So it looks like garage might be better interpreted as a categorical variable. So we're going to keep it as categorical. So what I'll do is just include garage up here. Remove this whole thing. And we can remove this. And this. Alright, and that's it. So that will sum today's video. Thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.